out.
I want to go over a very simple practical example regarding passing arguments to threads and all the concepts that we learned so far. So instead of having 10 threads, we're going to have only 2. And what I want the program to do is very simple. Is to sum up all the numbers in this, let's say, prime thread. Okay? And to do this, well, technically, it's not that difficult. We have to just split it in half. Right? We have half, or the first half of the array is going to be sent to the first thread, and the second half to the second thread. And then we're going to get back a value, a sum of all those numbers in the main thread, and then in the main thread we're going to just sum all the half sums together and we're going to get the final result. That's the basic gist of it. So how do we actually implement this? Well, the first step would be to change the number of threads, so we're going to have only 2 threads in this case. I have only 4 from, I guess, 1, 2, it's not, or 0 to 1, it's not going to be a very long lasting 4, but it's going to be there, and we still need this malloc because we're going to pass some values to it. And we need to figure out what we add in here, because I is definitely not correct, right? We want to start off, we want to pass the start index from which we want to sum half of the array, right? So I want to the first thread to pass the index to the first element, so that's very simple. But to the second thread, I want to pass the index to the, not the second element of course, but to the 6th element, right? So that whenever we are here, we just sum 5 numbers, and when we are here, we just sum 5 numbers from the array. Now, that means what I have to do here is say, instead of just I have to say I times 5. That means that when I is 0, we're just going to get 0, which is the first element in the array, and when I is 1, right, because 1 goes up to 1, it's gonna give you 5, which is the 6th element. That's perfect. Okay, so that's being taken care of. Now let's fix up this whole mess. So we don't really need the printf anymore. We don't want printf really. We just need to create this sum. So let's say here int sum equals 0, and let's create the for loop. Int I equals 0, I equals then. Well, we know we need 5 elements. This is hard-coded. You can change it to as many elements as you want. You have an array of 20, you can have here 10, and so on and so forth. I plus plus, and then sum plus equal primes, and then our index, but not quite because that index is just the initial index. It's going to be always 0 for the whole for loop. So we want to add this I in the mix as well. So if we got index 0 on the first thread, we get 0 plus 0 is the first element, then 0 plus 1 is the second one, and so on and so forth. And to note here, this I inside this for loop is not at all the same as this one. So these are 2 separate places in memory, values, etc. In fact, it might as well just change it for J so that we actually know what's going on. Okay, now we have the sum, that's amazing, but how do we send it back? Well, remember, this is returning a void pointer, so what can we do in this situation? Well, there are 2 options, I guess. We can malloc another place in memory and return that, while we also free our argument, or just return this place in memory that we have already dynamically allocated, right? So this is a really good way of handling dynamically allocated memory, is by just passing it to the thread and make sure the thread returns it back, so that you can then deallocate it in the main function. So now instead of calling free, we're actually going to make use of it after the thread has finished its execution, and instead return arg. But of course not arg without its value changed, because that's just our index. And I'm going to have to say here arg equals sum, and I'm probably going to have to pass it to a int pointer here. And now that's going to be correct. So the same exact syntax is now. It's now above. And then you can return arg, but with a different value. And where do we get that value? Well, we get it right in here, in this second parameter, which we can define in here. We can just say, let's say r from result, and we don't have to give it any value because this guy takes in a reference to our pointer. So if you take a look at the signature, it's a void double pointer, so just passing a reference to a pointer, and this pointer is going to be set to whatever we return here. Now that we have returned our argument, well, in here we know that we actually have inside r a pointer through the sum itself. So we can have here a variable called, let's call it global sum, initialize with 0 and just say global sum plus equals diref of r. And let's not forget to also free them. So a good rule of thumb is that wherever you have an malloc, you should have the same number of free calls. Right now we don't have any free calls, so that's bad. We have like 2 mallocs, one for each I. So I'm gonna call here a free of our R here that has been passed now. Right, so this guy has been allocated here, passed to the pthread create, passed in here, and then return back in here, inside R, and just we just write the value from it, and then we freeze that method. So now if we try to, well, I guess first we should print that the global sum, %d, \n, and just say global sum. And if I try to run this, you're gonna notice the global sum is 129. And that is actually correct. If you go to Google and you try to sum all this up, it's just gonna give you 129. Now to also make sure that everything is right, let's do a printf statement in here as well. So let's printf local sum %d\n sum. Now if I try to run this, we should get 2 different sums, and 28 and 101. 2 plus 3 is 5. 10, 17, and that's 28. That's correct. Then this is 30, 49, 72, and 101. Okay, so these are the correct answers. It's perfect. It's working so far. Amazing. Now there we have one warning here. I guess we should, yeah, let's custom this for a double pointer to avoid any warnings. That should be fine now if I launch this again. Yep. And there you have it. You have your sum computed in a multi-threaded fashion. And that's really all there is to this. There are other solutions, of course. So really, instead of returning the local sum, we could have just summed it all up in the thread here, but then we would have needed to use a mutex, and we had to have our sum global, it's a global variable, so this was, I feel like, a nicer implementation, but definitely you can try and do that. That would be interesting to see. And, well, if you do have any questions, leave them down comments below or on our Discord server. Of course, the code is going to be found on our website, which link to it you're going to see down in the description below. Thank you so much for watching. Take care.
அது எவ்வளோடா லேப்டாப்பு? லேப்டாப் எவ்வளோண்ணா தருவானுங்க?
உனக்கு எத்தனைக்கு வேணும் கேளு, தருவாங்க மாட்டாங்க நான் சொல்கிறேன். எத்தனைக்கு வேணும் கேளுடா, அப்போ சொல்கிறேன்டா நான். தருவாங்க மாட்டாங்கன்னு கேட்டு பார்த்து.
ஓகே.
கேட்டியா?
கேட்டு பார்க்குறேன். கேட்டேன், எவ்வளோன்னு கேட்டார். தெரியலன்ட்டேன்.
நீங்கள் சொல்கிறதா ரேட்டுன்னு சொல்லு. சொன்ன ரேட்டுக்கு கேட்டு வாங்கி பேச வாங்குறதா? சரியா? எது கம்பெனி யூஸ் கேட்குறாரா இல்லை எது கேட்குறாரு?
கம்பெனிக்கு தான் அந்த ஆளாக யூஸ் பண்ணுறாரு.
அது அவ்வளோ யூஸ் ஆக மாட்டா.
கபில ஸ்டேட்டஸ்லாம் போட்டுக்கிறாங்க. அதுதான் நான் டெய்லி யூஸ் பண்ணிட்டுருக்கிறேன்.
அப்போ ஒரு லேப்டாப் எனக்கு அனுப்பிவிடு கொரியரில்.
நான் அது இங்கே வந்து யூஸ் பண்ணுவேன், ரூமில் வந்து யூஸ் பண்ணுவேன்.
இதெல்லாம் கொழுப்பு தானடா டே.
எல்லாம் கொழுப்பு தான்டா.
10,000 விட்டு லேப்டாப் வச்சுக்கோ.
எல்லாம் யூஸ் பண்ணதானடா ராம, புதுசு இல்லைல்ல? யூஸ் பண்ணதானே, புதுசு இல்லைல்ல?
புதுசு எல்லாம் இருக்காதுடா. இன்னும் இப்போ ஓப்பன் பண்ணால் வச்சுருப்பானாடா. யூஸ்னா நல்லா லைட் யூஸ் பண்ண தான் வாங்கி தரேன்னு சொல்லி பெஞ்ச் மார்க் இது போட்டு செக் பண்ண முடியுமா? யூஸ் பண்ணிக்கிறாங்க பண்ண முடியாதா?
அதெல்லாம் பிரச்சனை இல்லைடா, யூஸ் பண்ணி அப்புறம்
என்கிட்ட யூஸ் பண்ணிடுவானுங்க.
குட் கண்டிஷன் தானே எல்லாம்.
ஒரு நாள் வாங்கி வச்சு யூஸ் பண்ணால் கிடக்குது. நல்லா ஸ்பீக்கர் இருக்கிறதா சார்ஜ் நிற்கலான்னு பார்த்தா கிடக்குது. என்ன வேணும்? எத்தனை லேப்டாப் வேணுங்க முதல்ல? சரி பாரு, நானும் போய் படுக்கிறேன்.
ஓகே ஓகே. அண்ணன் என்ன பண்ணுறாரு?
அண்ணன் மாட்டுங்க விட்டுக்காரு. பேலிவுன்னு படம் எடுத்து வச்சுக்கிறேன், போய் பார்க்குறேன்.
பேயா?
பேலிவுக்கு பேலிப்டா.
பேலிவா? ஓகே.
பன்னிரண்டு இருக்கிறான். பேலிப்டா.
பேலிவா? ஓகே ஓகே பார்ப்போம்.
அதனால நான் கண்ணாடி படம் தான் ரீல்ஸ் பார்த்துருப்பேன். நம்மளே அந்த படம் பார்க்கணும் வச்சுருக்கோம். நீ டைம் தான் பண்ணுறோம். யூடியூப்லேயே இருக்குதுடா, ஏற்றி பாடுறோம்.
நான்லாம் பார்க்கலப்பா. நான் அந்த டெட் பாயிண்ட் சொசைட்டியே 3 தடவை பார்த்தேன். டெட் பாயிண்ட் சொசைட்டியே 3 தடவை பார்த்தேன்டா.
என்னம்மா எல்லாம் எனக்கு வீடு அவனும் பார்த்துட்டா. ஆன்லைன் பார்த்துக்கலாம். அம்மா வாட்ஸ்அப் பூமர் வாட்ஸ்அப்
எட்ரா கூப்பிட்றாரா அவரு? சார் ஸ்டாப்லடா. ஹலோ சார். ஆமாம் சார், அவங்ககிட்ட கேட்டால் அப்புறம் அதிகமாக சொல்லுவாங்க. மேக்ஸிமம் 10K கொடுக்கலாம் சார். ஓகே சார். ஓகே ஓகேங்க சார். அப்போ எவ்வளோன்னு சொல்கிறாங்கன்னு கேட்டு உங்களுக்கு ஃப்ரெண்ட்ஸ் தான் சார், ராமோட ஃப்ரெண்ட்ஸ். அவங்க காலேஜ்லலாம் கொடுத்துருக்காங்க சார். அவங்க ஃப்ரெண்ட்ஸ்கிட்ட வச்சுருக்காங்க. ஓகே சார். அப்போ 2னா ஓகே சார், கேட்டு பார்க்குறேன். ஓகே ஓகே, தேங்க்யூ. பாய். 8 ரூபா.
ரூபாய்க்கா கேம் பார்க்குறேன்.
யூஸ் பண்ணாதாலும் பரவாயில்ல. ரெண்டு வேணுமாம்மா? 2. ரைட்டு. போய் தூங்குடா, படமெல்லாம் காலையில் பார்ப்பியாம்மா?
அவ்வளோ தூங்குறேன்.
பாய் பாய்.
turning the local sum, we could have just summed it all up in the thread here, but then we would have needed to use a mutex, and we had to have our sum global as a global variable, so this was, I feel like, a nicer implementation. But definitely you can try and do that. That would be interesting to see. And well, if you do have any questions, leave them down comments below or on our Discord server. Of course, the code is going to be found on our website, which link to it you can. In today's video, I want to take a look at the pthread mutex try-lock function and what it actually does and what is different between it and the lock function, the one that we used previously. To do that, I'm gonna have to first create at least, let's say, 4 threads, and I just want to see the behavior of pthread mutex lock first. So, I'm just gonna create a very simple program that does exactly that. And here inside the routine, what I want to do is simply lock a single mutex by all the 4 threads that we have created and print a message and see what happens. So, repeat it. Alright. And then simply just call pthread. So, we're going to create here. Alright, and then simply just call pthread mutex lock on our mutex, and of course also call unlock after we are done. And in between, we're just going to print a simple message that we got the lock. And after we got the lock, let's say it does something that is quite time consuming. So I'm going to just simply call a sleep here instead of actually doing something that's time consuming. Suppose that's something there. And if I try to run this, think about what's going to happen, what's going to show on the terminal. Well, simply because we have 4 threads doesn't mean that we're not gonna get 4 got lock messages. It's just that we're gonna get them in succession of 1 second, one after the other, because what's gonna happen? Well, all 4 threads are gonna start executing, right, the same exact function, but only one of them are gonna be able to lock that mutex. Right? The rest are gonna have to wait. Okay, and then only after that single thread that I got the lock, unlock that mutex, then another thread can continue, and so on and so forth. That's what's basically happening here. Alright, then what's so different about try-lock? Well, if I change this to a try-lock instead of lock, well, this is a bit more tricky, because with try-lock you are trying to lock the mutex. It's not guaranteed that you got it, but if you did, that's great, but if you didn't, you shouldn't be executing the code in the critical section. Therefore, you should check the return value of try-lock, always. So the return value of try-lock is 0 if you got the lock, or is something else if you didn't. It's actually busy if you didn't get the lock. So we can say here if try-lock equals 0, then we can execute this printf, this sleep, and of course if we got the lock, we should also unlock it. So that unlock code.
படத்துக்கு தான் நீ நானு உங்க அக்கா நாங்க ரெண்டு பேர் படுத்திருக்காங்க இங்கிட்டு 2 பேர் படுத்திருக்காங்க அங்கிட்டு 2 பேர் படுத்திருக்காங்க இல்ல ராம் வந்து சொல்றேன் என்ன தியேட்டர்னு சொல்றேன்னு இருக்கான்
என்ன படம் ஜிடிஎன் தான் வரேன்
போடுறான் உனக்கு சேர்த்து போடுறான் ஜிடிஎன் இல்லைன்னா டிசி போவோம் டிக்கெட் இல்லைன்னா டிசி இல்ல 3 படம் இருக்குடா ஜிடிஎன் டிசி விஸ்வநாதன் சென்ஸ் எதுக்கு வர
விஸ்வநாதன் சென்ஸ் சூரிய படம் அந்த ரெண்டும் ஓகே
டிசி என்னடா உனக்கு
அது நல்லா இருக்காதுண்ணா
அடிப்படா சரி
விஸ்வநாதன் சென்ஸ்க்கு டிக்கெட் இருக்குடா டேய்
அது
அப்படியா
அப்படியா
That's exactly the same. Okay, and let's say on else we can say that well, if it's not 0, that means it's the constant EBZ, which it's actually I don't know the H here. If I type in EBZ, yeah, it's 16. So that's what we got. We get if our try-lock function tries to lock the mutex, but it's already locked. Okay, and just print out the message saying that didn't get locked. Okay, that's it. Now if I try to launch this, think about what's going to happen. In this case, we might notice that you don't actually get 4 got lock messages. You only get 1 got lock message of the first thread that got the lock here, but the rest tries to get the lock that failed, and the execution continued on the else branch because the result wasn't 0. So it just continued with the lock. And that's the difference between try lock and lock. Basically, one of them is instant and the other one is going to be waiting. Okay? So lock is going to be always waiting until the mutex is unlocked, but try lock is just going to say, okay, well, are you locked? If you're not locked, then okay, that's fine, you can lock and execute the code. But if you're locked, then that's also fine. I'm just gonna return, I'm not gonna wait, I'm gonna return out of the function with a number that's different than 0 here, and the programmer knows what to do from there, right? Like I did here. And that's really all there is to it. I think it's a very simple concept to grasp. In a future video, we're going to take a look at certain examples that make use of this try-lock function because it's very interesting and has some nice uses. Although the examples are quite a bit more complex than the usual, it's probably fun. Alright, thank you guys so much for watching. If you do have any questions, leave them down in the comments below or on our Discord server. Of course, the source code is going to be found on our website, link down in the description below. Take care. In this video I want to talk about randomness and how to get a random number in C. So first things first, you have to include the stdlib library, right, to get access to the rand function. So the rand function is called just like so, with no arguments, and it returns back a random integer, right? So I can just print here, print f, %d, let's say \n, and just the random number. And if I run this, we get 41. Random enough, right? It seems like it's pretty random, nothing fancy here. Now, there's one pretty big problem with this random number. If I try to run this again, you'll notice that we still get 41. And if I have, for example, multiple random numbers, I get these three numbers, and the first one is still 40. And if I run it again, well, you'll notice it again, just the same three numbers. Well, that's a big problem, if you ask me. So what's the issue here? Well, the issue is with the seed of that random number. When using a random number generator, for it to be somewhat predictable, it can keep the same results every single time you execute, right? So whenever it starts a new program, basically, the sequence of random numbers that it gives are always the same, unless we specify a proper seed. So, to do so, we have to call the srand function. And the srand function here takes an unsigned integer. And for example, as you can see here in the declaration, an unsigned int. And for example, if we try to give this function the seed of, let's say, 0, why not? If we try to run this, you'll notice that we get three different numbers. And that's because we have changed the seed that was previously there. In fact, the call that happens before any rand function is srand of 1. If we try to run this with the seed of 1, you'll notice that we get the same two numbers as if we didn't even have this function, right? That's because that's the starting point, that's the seed that gets initialized. Now, how can we make this function, this program, return three different numbers, random numbers, or pseudo-random numbers, every time we execute the program? So we don't want 40 or 41 every single time we execute, we want a different number. It's actually very simple. If we have the seed, if we can change the seed here, and if I change it to 3, we get different numbers. So, what we have to do here is have this number be variable every single time you execute. What's variable every single time you execute? Well, funny enough, actually time is different. So, if we take the sequence since the 1st of January 1970, then you can actually have randomness or pseudo-randomness every single time you execute. To do so, it's actually very, very, very simple. All you have to do is first include the time of each. Time of each here, and instead of saying srand of 3, what you want is, let's say, have a line t variable that says seconds from Apple, and that would be equal to the result from the function called time, and this time takes in a parameter, and that's a pointer. And that pointer really just does the function to store the result inside the variable. But we can give it null, so that we don't really need to store anything. So you just kind of, this function basically returns and saves it inside the pointer. So it returns the value itself and saves it inside the pointer, which is a bit redundant in my opinion, but still. So we have the seconds from Apple. Now if I actually use this here instead of 3, for example, if I try to run this now, you'll notice that we get, well, 1,850. Oops, nice. Now if I try to run this again, well, we get different numbers every time. 1,824. And you'll notice that they are kind of decent. Like, maybe the first number is a bit similar to the previous iterations, but the second and third are very widely different, right? So that solves our issue. Now the only thing that might really be important is that this thing is usually a 64-bit integer, and this accepts a 32-bit integer. So you might need to use a different type. But that's for another time. This already just works, and you can use it as is. In fact, you don't even need this variable if you really want to. You can just copy and paste this and be done. Very, very, very simple, right? And that's about it. I just wanted to show you why you would be getting the same random numbers every single time you execute it, and how you can actually change them. This works for every. In this video, we'll tackle what is a void pointer and how can we use it and what's the difference between it and a chart pointer. Alright, so first we start with the creative problem that we can solve. What I want here is, well, I have an array that I find here, and I want this array to be printed on the screen, and I want to see it in hexadecimal representation. Right, so to do this, it's very simple. Let's create a simple function and try to print it on the screen. Now, as you can see here, I created a function that what it does really, it takes in an array and the number of elements in that array and simply prints out each element of the array. Now, the way we print this out is actually a bit complicated, so I'll get a bit into it. Here we say, alright, percent %x says, alright, print it in hexadecimal format, print any variable in hexadecimal format, and print it on 8 characters, that's what this 8 is for, and also print zeros wherever you don't have anything to show, don't just print empty spaces, right? If I try to run this, so we can first actually call the function, we say array, and we have 4 elements now. If I try to run this, you'll notice that we get 4 sets of 4 bytes in here, right? Each pair of 2 digits is actually a byte representation. So if you notice, we get 16 in hexadecimal, that is 10, right? Then we get 31. 31 is 20 minus 1 in hexadecimal, and that's correct. Then 1/2. Then 32 is just 20. Then 65 is just 41. You can check that with a hexadecimal calculator. Now, what I want with this function is what if I have here long longs? So instead I have simple long longs. Well, if I try to run this, I don't get the expected result. I get still actually 4 pairs of 4 bytes, but I actually have 32 bytes since each long has 8 bytes, and 8 times 4 is 32, right? So this is actually 32 bytes, and what we're printing here is only, well, 4 times 4, okay? Now I want a better version of this function, so, and I want it to be able to take in any sort of variable, a long, a short, even a chart for byte representation, anything, and just print it on the screen, and byte by byte, print every single part of the memory as hexadecimal representation, right? How can we do this? Well, that's actually very, very simple. In this case, we can actually use a void pointer. And a void pointer basically says, okay, you can give me a pointer to anything, right? Be it an int pointer, a long pointer, a short pointer, a struct of yours pointer, whatever it is. And I'm gonna try to make sense of it, right? Okay, and now, if I try to run this, or actually just compile it, you'll notice that we get an error. It says dereferencing void pointer. Why is that an issue? Well, r of I actually dereferences that pointer, right? It's like saying r plus I, and then dereferencing. Same thing. So since this is a dereferencing, we're not allowed to really dereference the void pointer because by definition we don't know what that is. But the key thing here is that we want that void pointer to be of size 1 when printed on the screen, right? So what can we do? We can actually dereference it before casting it to a chart pointer, right? So you can say in parentheses chart pointer r and then of r, right? So we're first casting it to a chart pointer and then dereference it, right? Because we cannot dereference void pointer. Now if we try to run this, well, you notice that we don't get the expected result. We just get, well, we get the 16 here, which is still 10 in base 16, which is nice, but we don't get all the other ones. How can we do that? Well, first things first, we have to decide here what we're printing. Really, if we're printing just one single byte, that means we're printing 2 base 16 digits, right? So, really, if we're printing just one, still 10 in base 16, which is nice, but we don't get all the other ones. How can we do that? Well, first things first, we have to decide here what we're printing. Really, if we're printing just one single byte, that means we're printing 2 base 16 digits, right? So that means that we have to change this 8 to 2, right? Another problem is when we're trying to send it the array, we're actually sending it n elements, right? But since it's a void pointer or chart pointer of, let's say, 3 is actually the 3rd byte. But remember, we actually have 32 bytes in here. Having 32 bytes in here means that we have to send 32 bytes here, since this boils down to a void pointer, right? And pointer addition works on the level of the type it's referenced. You can check out the video up top that I was referencing. I talk about addition between pointers and what can we do. Alright, so now we know that we have to pass in 32 bytes here. Well, we can say 4, we can just say 32, but to be more specific, we can say simple 4 times size of, well, long, right? Because that's what we're printing. So that's 4 times size of long is actually 8. Right? We have 64 bits in a single long. That means that we get 32 bytes in total. Now, if we try to run this, you'll notice that we get 32 bytes in here. You can actually come one, but we have to get 32 bytes here. And we're actually getting every single number here, albeit in a little endian representation. So here we have, for example, the 10, which is 16 base 10. And then we have 7 bytes. Remember, the first byte is still, 7 bytes are 0 because there's nothing there. Then we have 1F, that's 31. It's basically 20 minus 1 in base 16. Then we have the 32, 20. Then we have 65, which is, well, we're going to 41. So we got basically the whole array printed on the console, which is amazing, using this void pointer. Okay. Now, what's the advantages between using a void pointer or just using a chart pointer? Well, the advantages are pretty nice that at compile time you get a few checks. Let's see what happens if I change this to a chart pointer. Because right, a chart pointer is technically still a void pointer because a chart is just 1 byte. Okay? But if we try to run it or just compile it, you'll notice that we get here a expected chart pointer, but argument is of type long int pointer. Right? And that's what void pointers are about. They're about actually not giving us an error whenever we're trying to passing it to a function and dereferencing. Yeah. So you have to, in this case, if it's a chart pointer, you actually don't have to cast it. But that's kind of dangerous because, well, what if you don't want to automatically cast it? You don't know what the type is behind all this, right? So it's kind of strange. It will work, sure, but it's a little bit dangerous, right? And the compiler kind of protects ourselves from actually passing in a different type of its requirement, right? So that's what I want you to take from this video. Char pointers are pointers to the characters, but void pointers are actually pointers to anything. Anything you want to give it, be it an array of longs, be it an array of shorts, be it an array of ints, anything goes, as long as you cast it beforehand, right? If I try to run this, it's going to give me an error that I cannot actually dereference a void pointer. And that's correct, because I first need to say, okay, well, first consider it a char pointer, and then dereference it. Let's say like this, and then like this. If I try to run this now, it's correct. It gives me the expected result. So I hope you got this out of the video, and thank you for watching. See you. See you guys next time.
One concept that I see messing up new programmers all the time is void pointers. They've just begun to understand pointers, and then this new type shows up that they really can't use correctly, and it just messes everything up. My name is Low Level Learning. I teach people how to write faster and safer code, and today we're talking about what a void pointer is, why they exist, and how to deal with it. Let's jump right in. First, we can talk about pointers in general. What are pointers? So pointers are actually really simple, despite how often they confuse new programmers. A pointer is just a variable that contains the address of another variable. So for example, we have a variable int a that is an integer variable. We'll say that its value is equal to 4. So now that value a contains 4 bytes represent the number 4. So later on in the code, we can say that int star key a, that means we have now a variable that points to an integer. It is an integer pointer because it contains the address of a. Now I'm going to say that PA points to a. I have questions like, why do you use pointers? And in case we use integers, like this, I'm pointing a pointer to an integer. That's actually a very question. We really need to use pointers here because the size of an integer is 4 bytes. That's actually within the word size of our architecture. And it's on a machine that's 8 bytes. So this 4 byte type can actually pass around by value. I can make a function called int to do a thing, and it takes text, and I can return, x plus 2. Right? I don't need any special pointers. I can pass a by value. I can literally pass in a equals do a thing on a, and that'll add 2a over 6. But what if you want to use values? What if you want to use variables that were bigger than the word size, and that wasn't an integer? So it's not using a 4 byte value of integer. What if I have a structure that is greater than the word size, greater than 8 bytes? And here I have a structure called person that has 16 8 bytes of data, has a 4 byte integer ID, and has 64 byte buffer for its name, for example. So if I want to do any operations on person p, I would pass p by reference. I could not pass by value. And the way we would handle that is we make a function that's called, do a thing. Only now it takes a person pointer called p person. And we can say that inside this function, p person ID equals 0 or something. And then maybe we memset the address of p person name 64 bytes or 20 of 64 bytes. Maybe this is like our initialized person structure. Because person is such a large structure, we have to pass it by reference. So we do that. We call the function. We say do a thing on p. Awesome. So that's pretty straightforward, and we can check return value, int ret equals to a thing. Obviously, this will return some stats, so it'll say return 0 here. So then we talked about pointers for a minute. Now, what is a void pointer? The whole point of this video. What does a void pointer do for us? So when you actually have a pointer, and you have, go back to our int a example, we have int star pa, is the address of a. If I wanted to dereference or look up the value at an address, I would add a star character, which is the dereference operator, which tells the computer to go to that address and get the value that lives there. Well, the question is, how much data do we get? We need to go get the value at an address, but a lot of structures are bigger than just 1 byte. As I said before, the int value is actually 4 bytes wide. So by dereferencing the type, I use the type information as defined at compile time to tell the computer how far out to go. And the reason this is so problematic with the void pointer is because the void type does not have a size. Because of that, if I say that void pointer and call it VA is equal to the address of A, I'm actually unable to dereference VA. Well, the compiler's open, I'll show you that. So I get an error here, invalid use of void expression. The reason is the compiler is trying to make an assembly instruction to reach out to the address that's contained in our pointer variable and go get that many bytes. But the problem is it's a void type. It does not know how many bytes to get. So you're probably wondering, why does this variable type even exist? Why would we create a type that does not have type information? It breaks all our code we can't use. When we use functions that give us memory or free memory allocation functions like malloc, for example, all of these pass around a void star as a type, right? So malloc returns a void star, calloc, realloc array, all use the void star type. And also when you free, you pass in a void star type. The reason for all of this is because the C language is giving you the power to tell the compiler what type is stored there. So let's kind of go through that in a practical example. So let's say I wanted to make room on the heap for my person structure. Right now my person structure is all being contained on set. Let's delete all this, and I say that I have a person pointer, right? So it's a person pointer. We'll call it p person, and I want to malloc it from the heap. And how big do I malloc? That's the input to malloc, right? Is the size I'm getting. I'm going to malloc the size of a person. Well, by default, the equal sign will throw a warning if you have W error enabled / error, because the malloc type is returning a void star, and we are implicitly casting it to a p person type. So what we actually have to do is tell the compiler, hey, I'm aware this returns a void star type, but I need to convert it to a p person type. All we're going to say is a person star, and by putting it in parentheses like this, just a type, we're going to call it a type path. So the type that comes out of this is being converted at compile time to a person star and put into our variable. And obviously we have to check our value, right? We say if null double equals p person, and we say, puts the heap failed, run away, or whatever, and then we return what this program failed, we can use our code. And then if we want later on the code free it, we then free p person, and this does take a void star as input, but the implicit caster is actually okay. Don't forget I'm using keep includes lib because that's the library that contains functions. And there we go. So now we compiled the pointers program with no error. So what is a good idea to use a void star? Well, a void star is meant to represent what's referred to as typeless memory, right? So if you are mounting from the heap where you have a variable that is undefined and its type represents a raw block of memory, that's where the void pointer makes no sense. And the minute that you know the type of that variable, you should then be passing it to that type or just use that type in general. Like for example, because this function is a, let's say that this is the initialized person function, right? We should never be passing a void star pointer and then saying person p person equals person star of pointer, right? Like if we know the type of the memory ahead of time of person star of pointer, if we know the type of the memory ahead of time, we should never use void star. We should always include type information in our code as often as possible. But in cases like this where we are mallocating and freeing raw memory that is not known by the allocator at the time, we can include type information, then we just use the void star the way it's intended and then cast it and get that memory. Now another question people have is why do header files exist? Why do I even have to include standard IO.h, standard lib.h? If you're curious about that, like I was, go watch this video, and find out. See you guys later.
Today I want to talk about pointers, specifically pointers that don't have type information, are also known as void pointers. Hey everybody, welcome back. Today's video is for the beginners, for fairly beginner programmers out there who think that you finally wrapped your head around pointers, but then you see something like this and you're not really sure what to make of it. Because this causes a serious moment of pause for a lot of beginners. So I thought today we would talk about what a void pointer is, why you might want to use one, and we'll also talk about some examples where you may have already used a void pointer and you just didn't realize it. Also at the end I'm going to talk a little bit about a subtle difference between C and C++, might save you some time. But first, a big thank you to all of you who support this channel through Patreon, buying merch, and online classes. Also for those of you that are curious about where you can get example code for my videos, you can get that through Patreon, and you can get access to my monthly office hours. So now back to void pointers. If you look long enough into the void begins to look back through you. I don't know if Nietzsche was talking about new programmers, but sometimes the concept of void takes a second to get a grip on. Now, the first time you see void is probably when you are looking at a void function, maybe something like this. We make a quick function, and let's just say it's a simple function that prints out the word hello with a new line character. Nothing complicated about that. So in this case, the void simply says that this function does not have a result type. It doesn't produce a result. It doesn't give us a value when it's done. So if I come down here in main, I can definitely call say hello, and this is going to work just fine. Now, let's make sure just by coming down here and compiling with my makefile. I am using a makefile. You can check it out here. Nothing complicated, just a really basic makefile. If you haven't seen make, be sure to check it out on my other videos that deal with make. And actually, hold up really quick. I just noticed I was editing my C++ example. Let's do this over in C and compile that one. We'll come back to C++ later. But if I run example here, then you'll see that it works just fine. It prints out hello, so no worries. But note that I can't do something like this. I can't say result equals say hello like this. If I try to do this, I'm going to get an error because it says, hey, look, you're trying to assign to an integer a value void. It doesn't have any type information. It's not a variable. Simply, the compiler just doesn't know how to take nothing, no variable, no result, and produce an int out of it. So it gives us an error. So hopefully that makes sense. Hopefully that's straightforward enough. And I'll leave this up here, but so what about if I come down here and say something like void star p? We understand what it means for a function to be void, meaning it doesn't return anything, but what does it mean to have a variable p, which is a pointer that points to void, which maybe up till now we've thought of as nothing, so is this a pointer to nothing? Okay, so calm down. You see, at least in this case, it's probably more helpful to think of void as meaning no type rather than nothing. So we can think of this as a pointer, but we have no type information that is attached to that pointer. So the compiler is storing an address for us in memory, but it's not making any assumptions about what is stored at that location in memory. But really what I want to emphasize is that it is still a pointer, just like any other pointer, it stores an address. And just to make this clear, what I want to do is to come down here and we'll just add a little bit to our program. First thing I'm going to add an int pointer, call this p2, or let's call this ip. This might be the kind of pointer that you maybe were introduced to. And let's come down here and add a couple printf statements. We're going to say the size of a void pointer equals either zu, because we're using memory sizes. It's a good habit to get into. And we'll do size of void pointer. And then let's do the same thing with our int pointer. So we'll do p right here, ip right here, and change this to be an int pointer. Okay, so now we can compile it, we can come down here and run it, and you can see that both of these are the same size. At least on my machine, we're looking at 8 bytes per pointer because they're both simply storing an address, and on my machine, an address is 8 bytes. And since these pointers are basically the same, we can do something like I could say p equals ip, right? And just assign one address value to another. And just to see this in action, let's come up here and let's make an integer, we'll call it x, and assign it to a value, let's say it's brief. And then I'm gonna come down here and take my int pointer and assign it to the address of x. Now note that I could have just done the same thing with p. I could say p equals the address of x. That's gonna work just fine too, but let's not do that right now. We'll come to that later. My point right now is that we have a value here, and we should have an actual address being assigned to IP, and then when we assign p to the IP, we should end up with the same addresses. So just to verify that, let's come down here and get ourselves another printf statement. It's going to be p points to %p. If you haven't seen the %p format specifier, this is simply there for printing out addresses, which is exactly what I want to do right now. I'm going to print out the address of p and the address of IP. And now if we come down once again, we compile it, and if we run it, you can see that we get the same address for both pointers. So I hope at this point it's making it clear that they're both pointers, they're both storing an address. In this case, they're storing the exact same address. So what's the difference? Well, for one difference is because we have type information around it, I can come in here and I can say IP, star IP, I can dereference it and say this equals something else. So let's say coffee. Okay, so this is going to store the integer coffee at the address that IP points to. But I'm going to run into trouble if I try to do the same thing. So let's say I do star P equals and I give it its own value. If I can type beef, and this is going to give me a little bit of trouble. If I come down here and try to compile it, it's going to say, hey, wait a minute, void is not assignable. You can't assign something to void. You have no type information here. So the first thing you need to know about void pointers, I guess, is that you can't dereference them, or at least you shouldn't dereference them in general, because you can't do much with void. But of course, this is only a minor inconvenience because, as I mentioned in some previous videos, C is not a type-safe language, so we can just add a cast in here. And what I'm saying here with this cast is I'm saying I want you to treat P as though it were an int pointer and then dereference it. And now with this added cast, this line is now going to work just fine. So again, once more, let's just double check. Let's make sure this is actually working, and we'll print out our contents. We'll add a %x specifier, because I'm going to print out in hexadecimal, and we'll come down here and do star P and star IP. Once again, I am going to need the cast, because otherwise it would complain to me saying it doesn't know what to do with this void pointer. And now we come down and compile it, and if we run it, you can see that both of these memory addresses are pointing, both of these addresses are pointing to the memory containing dead beef. Now let's pause here really quickly to make sure this all makes sense. Some of you may be wondering about what happened to coffee that I wrote up here in the location pointed to by IP, and I did this on purpose because I wanted you to remember that these two pointers are at this time pointing to the same location in memory. So the last write to the memory pointed to by P, that overwrote the previous values in that memory, and both pointers are pointing to the same thing. So they only are showing the last thing that was written. So just to illustrate this, just to try to tease this apart, let's now make them separate. So instead of assigning P to be IP right here, I'm going to take this out, and let's come up here and make another int Y, and I'm going to assign P to be the address of Y. So now with just that subtle change, that very small change, I can come down here and I can run it, and now you can see that we have different addresses and different values because the two pointers are now pointing to two different locations. Okay, so that's cool, but why would we ever want to use a pointer with no type information? It just seems like it makes more work because you have to keep casting things, and it's just limiting, right? And the answer is that basically anytime you want to store generic memory addresses, basically when you want to store an address but you don't really care what type it points to. So one example that you're going to see a lot is when you use a memory allocator. So let's say instead of assigning P up here to the address of Y, let's say we come in here and say malloc size of int. So this is just saying, hey, I want you to dynamically allocate on the heap a block of memory that is integer sized, and then we're going to assign it to P. And then of course we should come down here at the end and free P once we're done with it. And of course this would work with our int pointer as well, but let's just take a look before we get to all that. Let's just look at the man page for malloc. Sorry. malloc. So this is showing us the malloc and free man page. We can see, and of course, calloc, realloc, and realloc array. But if you look closely here, notice what malloc returns. When you ask for memory, what you're doing is you're saying, hey, I want a certain size block of memory. Malloc doesn't really care what you're going to put in that memory. It just cares what size it is, and it knows that you're not really going to care. You just want the pointer back. Malloc is trying to be generic, so malloc returns you a void pointer. And of course, up here in our program, we could use malloc with a non-void pointer, and we'll get to that in just a minute. But first, before we finish with the man page, if you look at free, similarly, when we're done with the memory and we're just trying to like give it up and let somebody else use it, notice what we pass in. We pass in a void pointer again, because again, free doesn't really care what types you put in that block. It just wants to reclaim the block. So just give me the address. I don't care what's actually stored there. Another quick example, just while we're looking at examples, is memcopy, which we looked at in a recent video. That one involved an angry squirrel, just in case you haven't checked it out. But notice again here that memcopy is using void pointers, and the reason is it doesn't care what you store there. It's just give me an address. I'm going to copy the memory. I don't really care what it is. I'm just going to copy bytes. So again, the point here is anytime that you're trying to work with an address, block of memory, you want to store a pointer, but you don't care what it actually points to, then a void pointer is a really good option. This will allow you to, for example, if I wanted an array of pointers and I wanted to have them each pointing to different things, I could do that with void pointers. So, but now let's just tweak this a little bit. Let's get out of here and let's come in here and tweak things to make it work a bit more how we usually do things in our programs. Because usually in a program, if I knew that I wanted to have an int here, I wouldn't have a void pointer assigned to the result from malloc. Instead, what I would do, and let's just swap these two. So we'll have p be assigned to the address of x, and we'll come down here and we'll have the integer pointer now pointing to or assigned to the result from malloc. And I should come down here and free ip. Okay, so now at this point, I do have an unused variable. We'll get rid of y really quick. And if we come down, now our example works just like it did before. It doesn't really matter. We did change up the addresses, so now IP is on the heap rather than P is on the heap, but otherwise, basically we got the same thing. But the reason I bring this up is this highlights a difference between C and C++, but I just want to point out. So let's quickly just take this over to C++, and now if we compile it, you notice that we have a problem. You see, when C saw me assign a void pointer coming from malloc to an int pointer, it was like, cool, people do that all the time. That's what people do with malloc. But when C++ saw it, it was like, hey, those aren't the same kind of pointer. Do you think they're aware of that? You see, C++ is a bit more of a worrier. So in C++, we would have to come up here and add a cast to an integer pointer. And now if we come down here, it's going to compile just fine. And in case you're wondering, it will run just the same. And I just want to make it clear here that I'm not saying that one of these approaches, the C approach or the C++ approach, is better than the other. I do wish they would agree on one common way and do the same thing, because it would mean a little bit less for us to keep track of in our heads. But I really think this is just a reflection of the two languages' individual personalities. C over here is going to allow you to write slightly more concise code, while C++ over here is going to force you to acknowledge when you assign a pointer of one type to a pointer of another type. And that's not a bad thing, because that's actually that's the source of a lot of weird bugs. The main thing is to be aware of it, and if you're writing code that needs to be portable to both C and C++, then just include the cast right here. That will create more portable code because C doesn't mind. C's happy with that cast, but C++ requires it. So thanks for looking into the void with me today. I hope you learned something new. Please like, subscribe, go on a clicking spree. Just click on everything just to let the YouTube algorithm know that there's something interesting going on here. And until next week, I'll see you later. Today we're talking about one of the main reasons why
சொல்லுங்கண்ணா.
ஏய் லட்சுமணா,
ம்
உங்க அக்கா அவன்கிட்ட ஏதோ பேசணுமாடா?
என்னண்ணா?
டேய் ஒன்னும் பேசுறதெல்லாம் இல்ல, நான் ஸ்பிளிட் போட்டு விட்டுருப்பேன். கரெக்டா தான் டிக்கெட் போடுறதுக்கு.
ஜிபேலையா?
டேய் நான் சொல்றேன், ஒரு தம்பிக்காக ஒரு ஃப்ரெண்டுக்காக எல்லாம் காசு போட்டு போடு லட்சணா ட்ரீட்டுக்கா.
என்கிட்ட காசெல்லாம் இல்ல, நீங்க நினைக்கிற அளவுக்குலாம் இல்ல. இப்பதான் எல்லாத்தையும் செலவு பண்ணி
185 ரூபாயாண்ணா?
அத்தனை செலவு.
என்ன புடுங்குற செலவு?
13,000 ரூபாய் பிஜிக்கு மட்டுமே.
பிஜி கட்டினா சொன்னீங்கன்னா செருப்பால் அடிப்பேன்.
வேற உங்க அப்பனா வந்து இதெல்லாம் வாங்கி கொடுத்தான், பொருள் எல்லாம், பேஸ்ட், பிரஷ், மண்டைக்கு ரோஸ்.
உங்க பெத்த அப்பன் தானே வாங்கி, எங்க அப்பா எனக்கு வாங்கி கொடுத்துருக்கான். உங்க அப்பன் தானே உனக்கு வாங்கி கொடுக்கணும்.
அதான் எங்க அப்பா தான் வாங்கி கொடுத்துருக்கேன். இத்தனை அப்ப எங்க அப்பா அம்மாக்கு எவ்வளவு செலவு வச்சுட்டேன், கிட்டத்தட்ட 20K செலவு. அது பார்த்தா சாரி 7,000 ரூபாய்.
அது வந்து உங்க அக்கா வாங்குறது. அது வந்து நீ அதெல்லாம் கணக்கு எடுத்துனா இப்ப நான் கேவலமா உனக்கு கேட்பேன். 20,000 ரூபாய்க்கு நீ என்ன கிழிச்ச? 13,000 ரூபாய் பிஜி ரெண்டு, மீதி 7,000 எங்க போச்சு?
மீதி 7,000 தாண்டா எல்லாமே கொண்டு வந்து விட்ட பெட்ரோல் செலவு. உங்க அப்பனா தந்தா?
பெட்ரோல் எல்லாம் கணக்கு போட்டா எங்க போறது? கார் எடுத்து வந்துட்டு ஏன்னா
என்ன குழந்தைய கொண்டு வந்து விடுறதுக்கு? நீ உன் குழந்தைய கொண்டு வந்து விடுறதா இருந்தா கோடி விலையும் பஸ் ஏற்றி விட்டுருப்பியா?
உங்க ரித்திகா வீட்டுல எப்படி ஏத்தி விட்டாங்க?
நீ அதை சொல்லாத.
நான் அப்படிதான் சொல்றேன். அப்ப நீ அவங்க வீட்டை வந்து அவ்வளவு கேவலமா பேசுறியா? ரெக்கார்டை எடுத்துட்டாலும் நாளைக்கு உனக்கு போட்டு கட்டுவாங்க.
இல்ல எனக்கு புரியல. நான் வந்து எங்க வீட்டை பத்தி பேசிட்டு இருக்கேன், நீ உன் பொண்ணை பத்தி பேசுற. உனக்கு ஒரு பொண்ணு பிறந்து உன் பொண்ணை கொண்டு சென்னையில விடுறதுன்னா நீ
இப்ப அதே கதை ரித்திகா வீட்லயே அவளையும் யாராவது கொண்டு வந்து விட்டாங்களா?
நான் உனக்கு பிறக்க போற பொண்ணை பத்தி பேசிக்கிட்டு இருக்கேன்.
எனக்கு பொண்ணு பிறக்கணும் உனக்கு எப்படி தெரியும்?
அதெல்லாம் நான்
லட்சுமணா கோபி சாரோட சேர்ந்தவடா இவன்.
தோசிகாரி ஆயிருவீங்களா இருக்கே விட்டா?
ஆகத்தான் போறேன். ஏன் கௌதம் நீ மட்டும் வேலையை முடிச்சது கௌதம்?
உங்க அம்மாட்ட கேளு லட்சணா, வாங்கி போடு. நாளைக்கு காலைல வா, கையில தரேன்.
கையில எனக்கு வேணும், எனக்கு ஜிபேல இருக்கு.
ஹரிசனாலாம் வரலையாண்ணா?
காசு கொடுத்தனா சான்ஸ் வரும்.
சரி ஓகே.
ஏண்ணா ஹரிசனா வரலையா?
அவன் எங்கேயோ அவங்க அக்காவை பார்க்க போறான்டா.
சூப்பர். எத்தனை மணிக்கு?
இவன் வரான், சஞ்சய் வரான். 4:45 சாயங்காலம்.
சாயங்காலம் 4:45. அங்க பையனா போட்டீங்க?
பையன்டா போடக்கூடாது.
காலையில தானே சொன்னீங்க?
காலையில தான் சொன்னோம். காலையில இந்த டிக்கெட்லப்பா.
என்ன படம்?
ஜிடிஎன் தான்.
அப்பனா ஓகே ரைட். இருங்க வரேன், கீழே வரேன். என்னக்கா? ஜிடின்னா
எனக்கு உங்க அக்காவுக்கு பெட்ரா யார் ஜெயிக்கிறாங்களோ அவங்க அந்த படத்துக்கு தான் போனோம். நீ சொல்ல ஜிடிஎன்னா விஸ்வநாதன் சன்ஸா?
ஜிடிஎன் தானே. விஸ்வநாதன் சன்ஸ்னா அது என்ன கதைன்னே தெரியாது. யார அவனுங்க?
அவ்வளவுதான். நான் தான் ஜெயிச்சேன்.
தெரியாதுன்னு தான் சொன்ன. ஒண்ணுமே கிரிஞ்சு படம்னு சொல்லல.
அது கிரிஞ்சு படம் தான், எனக்கு அது தெரியும்.
அப்பனா தேவையில்லை, நீ வராத. நானும் ரித்திகாவும் சண்டே போறோம்.
சண்டே
நீங்க எங்கேயோ போங்க. யாரு கேக்குறா?
அவ்வளவுதான்.
என்னது
சண்டே நீங்க போங்க. நாங்கெல்லாம் ஒரு நாள் படத்துக்கு வரப்ப எங்க வீட்டு காசு இருக்குது. எங்க அப்பா எல்லாம் அவ்வளவுதான் கொடுத்துருக்காரு. 2 நாள் வரப்ப உங்க அப்பா அளவுக்கு கொடுக்குறேன்.
20,000 வாங்கிட்டு மறுபடியும் இன்னொரு படத்துக்கு போறியா நீ?
தேவையில்லை, நான் போல. வேணாம் கௌதம்.
சென்னையில் நிறைய இருக்கா சுத்தி பார்க்க. படத்துக்காக போறீங்க? எங்கண்ணா தியேட்டருங்க?
டிக்கெட் போட்டுறேன்.
சரி லட்சுமணா சரிடா.
நான் தியேட்டருங்க.
தியேட்டர்
நாவலூர் பரவாயில்ல. லைப்ரரி பக்கத்துலண்ணா. சூப்பர். லைப்ரரி பக்கத்துல தானே?
அங்கேதான்டா.
சூப்பர்ண்ணா. நான் காலையில லைப்ரரி போலான்ட்டு இருக்கிறேன். அப்படியே அங்கிருந்து ஜாயின் ஆகிக்கிறேன்.
கடவுளே கடவுளே. சரிண்ணா.
ஓகே பாய்.
பாய் பாய்.
பாய் பாய்.
Why your multi-threaded programs are way slower than they need to be. Welcome back, everybody. Today let's talk about something other than text. I've been talking a lot about text lately, about Unicode and white characters and all sorts of text stuff. Today I want to talk about speed, about threads, about fault sharing, which is something that you may not be aware of. Most new programmers are not, but which might make your multi-threaded programs a lot slower than they need to be. It's something that happens under the hood, and we're going to try to take a look at it today. So yes, let's look at some code. So this is where we're going to start. Yes, this video is going to contain source code, and as always, source code is available through Patreon. So huge thanks for all of you who support this channel. But I'm starting out here with basically just an empty main. Doesn't really do anything, except we're going to return exit success, and we'll need to include standard lib for that. So we have our empty main, basically, and some includes. I also have a makefile over here. Do check out my previous make videos if you are mystified by any of this, or if you just need to brush up. I do have a lot of make videos that can help out. I'm also going to be using pthreads. So you see pthread.h here. We're going to be using pthreads. If you are new to pthreads or just need to brush up, I have quite a few videos on threads on this channel. I'll put links down in the description. But for today, what I want to do is we're going to create a couple of threads, and I want to have threads working on multiple counters. So let's just say let's do UN64T counter 1, initialize that to 0, and let's make a second one called counter 2. And then I want to increment these, and let's increment these in different threads. So let's declare some pthread_t variables. We'll call them T1 and T2, and then let's just call pthread create address of T1, no attributes, just keep the default attributes, and then we'll have some thread function. We'll call it threadfunc, and then we're going to pass to that function the address of counter 1. Okay, we'll do the same thing with counter 2 and thread 2. Okay, and all I'm doing here is I want to set up a very simple example that's going to illustrate some performance issues that we run into. So let's implement this thread function up here. So we'll just come in here and it returns a void pointer, and we'll call it threadfunc because that's what I called it down in main, and void pointer some argument. So this is what all thread functions in pthreads looks like. We know that what we're passing in is a UN64T, so let's declare a pointer here called counter, and I'm going to assign it to be arg, and then let's also just put in a UN64T cast just to tell the compiler that we know what we're doing. And then in this function, so this just basically gives me a pointer to the type of thing that we're actually passing in, so that I can actually do things with it. And then let's just have a while loop, and we're going to just say as long as the counter's value is less than a particular threshold, we'll define that in a minute. But as long as it is, then we're just going to say whatever counter points to plus plus. Okay, we're going to increment our counter, and then once we're done, we're going to return null. And you've seen me do this in other videos. The whole idea here is I'm trying to create some work for the thread so we can actually time stuff. So let's just define threshold to be something large. Let's make it something like 10 billion, 1,000 million billion. And then you notice that I put return null because it returns a void pointer. I don't really care about the result. I'm not going to be doing something with the result, but it needs to return something, otherwise I'm going to get a warning. So then let's come back down into main because we need to actually wait for this counting to take place. So we're going to add a pthread join call, wait for T1 to finish, null because I don't care about the result, and then pthread 2. Okay, these two calls are just going to wait for the threads to complete. And then let's come down here and just print out the counter values just to make sure that it's actually doing what we want to do. Okay, so counter 1, we'll do the same thing for counter 2. Okay, so this seems like a good starting place. This is where I want to start the discussion. It's simple, it's straightforward, multi-threaded program. So what could go wrong, right? Hopefully we got a pretty good idea how this is going to work. And if I hadn't hinted at it, you would probably think this will be just fine. There's nothing really interesting to look at here other than we got two threads that are working on two different counters. But that would be a far less interesting video, so let's compile it and run it and just see what happens. Okay, so if we compile this, great, it compiles, good. And then if I run it, just make sure it works. So we end up with values that look reasonable. So our counters are all ending up at 10 billion. That is fine. But in this video, I really want to talk about performance. So let's run it again really quick and time it. And okay, so yeah, it took a while. It took about 40 seconds to finish. Well, you got, so your user time is 40, it took about 20 seconds to finish. But it had a lot of work to do, it had a lot of incrementing of those, like 20 billion increments. So that's a lot to do, it took its time. But is this fast, is this slow? I don't really know, but let's do something here. I just want to take this example and add one very simple tweak. I'm going to come here and I'm just going to add a variable. Let's just add an array of characters. I'm going to call dummy array, and let's make it 100. And we'll just initialize it to 0. Okay, so this should not change anything, right? We just basically declared a variable, an array. I'm sticking it between my two counters, and I haven't changed anything in the behavior of this program. It still compiles. We do get a warning. We'll just ignore that for now. But now let's run it. And if we run it again, what do we see? Okay, interesting. It took less than half the time it took before. So our program is running more than twice as fast as it did before. Let that sink in. All I didn't change anything except I added a little array right here in between my two counters. So what is going on? Now, remember those guys who complain that nobody needs those low-level systems courses like computer architecture and operating systems anymore? Well, here's one more example why they're wrong. Now, what is going on here is called false sharing. Of course, we know, and you got this from my previous videos, that shared variables that require synchronization are bad news for high-performance multi-threaded programs. But where's the sharing, right? I intentionally made two separate counters. I gave one to one thread, one to the other, so they're not sharing memory, right? Unfortunately, no. Sorry. Now for this, we need to understand how caching works. You see, your processor has a small amount of fast cache memory that it uses to store recently used variables. I'm oversimplifying things just a little bit, but the first time you access a piece of memory, it will go out and grab it from RAM, which is kind of slow, and it will bring it into cache. And then next time it will be faster because it just has to get it from cache, right? It saves it in this fast memory, and so the next time you access it, it gets faster. That's the main idea. But the cache typically stores memory in chunks, or sometimes they're called cache lines. And if two variables happen to be stored on the same cache line, then your two threads might end up spending a lot of extra time passing a cache line back and forth, making sure that it's all coherent. These are called cache coherence protocols. They basically make sure that if two cores are using the same cache line, that we don't get garbage data due to caching. And that contention over that shared cache line is going to slow things down. Okay, so just to illustrate things a little bit, let's change our program a little tiny bit, and I'm gonna come in here and just let's print out the address of our counters. So the address of counter 1 is %p, because it's a pointer, and then address of counter 1. Let's do the same thing for counter 2. Okay, I'm also going to just temporarily remove the dummy array, and if we compile it again and we run it, then you're gonna notice that these counters are right next to each other in memory, right? The one comes right after the other, and right next to each other often means on the same cache line. That's what's happening here, is we are ending up with two variables, counter 1 and counter 2, that are sharing a cache line. And that's why if I come down here and stick some data structure into the middle of them, this is going to spread them out just enough. So like if I add dummy array back in, and we compile, and we run it, now you can see there's a lot more space between these two addresses, and that's going to put them on separate cache lines, and it's going to remove all this fault sharing. Okay, naturally, of course, I am not about to recommend that you go around sticking arrays between your variables. That would just be plain ugly and make your code harder to read, and people would be super confused why you're doing this. And there are a few different ways we could go about addressing this. Today, I just want to show you one. It's a keyword in C that you might not be aware of that it might help. But first, before we get into that, I just want to also, it's good to know what size our cache line actually is. And so, unfortunately, I don't know of a good portable way to do this, but on Linux, which is what I'm running on, I can get it like this. So if I just say, I can call syscon. This allows us to read a bunch of system configuration parameters, and we just happen to have one that is on Linux available called SC level 1 dcache, that's for the data cache line size. So this is going to return a long, and let's call that cache line size. So this is going to return our cache line size. Yes, it's going to be the red squiggle because my Mac doesn't know about this thing. So like I said, it's not very portable, so let's just keep that in mind. It works on Linux, not portable. So depending on what operating system you're on, you might need to change this to something that works on that operating system. But for today, this will just work for illustrative purposes. So cache line size equals, and let's just say long integer. Okay, and then this will be cache line size port. Okay, like I said, I don't know a portable way to do this. If you do, let me know down in the comments because I have not found one. But if we run this, so we compile it and we run it, then you notice that our line size is 64, right? So we know that each cache line is 64 bytes. So as long as we spread out our variables, we put them in separate 64 byte chunks, then they're going to be on separate cache lines. Okay, so now that we know the size of our cache line is 64, I'm going to take out this dummy array because we're not going to need it anymore. And instead, I'm going to use the align as keyword macro, whatever, and put align as 64 on each of these, okay? You might occasionally hear people refer to memory alignment issues or align your pointers or whatever, and there are a number of different reasons why you might have to do this. This is just one of them. But what I'm doing here is I'm instructing the compiler to align counter 1 and counter 2 on addresses that are multiples of 64. So this is going to put them on separate cache lines, and it's going to spread them out. And now if we come down here, we can compile it, and let's just run it. And now you can see that these addresses are spaced out quite a bit more, but not quite as much as they were before. But you notice we get all the speed benefits we got from sticking that dummy array between our two.
ஊருக்கு போயிட்டார்ல
Our two variables. So this is one way that you can take these two things and make sure that they're aligned on separate cache lines. This will use slightly more memory, but really who cares? Most of the time we are willing to sacrifice an extra cache line, 64 bytes worth of data if it means that our programs run much faster. Also, like I said, there are other ways to prevent fault sharing. This is just one really easy one that I thought I'd show you today. Let me know down in the comments if you want to see more in the future, and we can pick those up in another video. But I hope this gave you something new to worry about, performance-wise at least, in your programs. I hope this helps in future projects, and until next time, I'll see you later.
Okay.